Alright, here we go with Chapter 7 homework review. We're rounding into the home stretch now and getting towards the end of the course, and this is going to be the first of the 3 chapters that will be covered on the third midterm coming up at the end of this month. Alright, so the average on this one was 9.69 out of 12, so pretty typical for this assignment over the years. We're going to go through about 10 or so problems that I identified as being ones that we had difficulty with for whatever reason. Most of them are topics we covered in class that we just want to rehash and look at some of the details on. There were a couple types of problems that we didn't really specifically mention in class, so I wanted to make sure to also go over those for your benefit. Alright, so let's get right into it. The first one here is dealing with change in internal energy. And when we think about changes in internal energy, we have this just one equation that deals with it, which is delta E is equal to Q plus W. And this is exactly what we're going to use here, because we have a system that's absorbing 109 kilojoules of heat from its surroundings and has 56 kcals of work done on it. And here we're giving you the conversion factor. 1 kcal is 4.84 kilojoules. We want to know what the change in internal energy is for that much heat and that much work. So here we're giving you Q and W directly. We know that there's some formulas we can use to calculate Q and W, but in this case we're telling you what those values are right in the problem. Now the only tricky part here is that we have 2 different units. So we want the energy change in kilojoules, but we're giving you heat in kilojoules. That one's fine. But we're giving you the work in another unit called kcal. Now, I didn't specifically mention calories in class, but calories is another unit of heat, and it's equal to the amount of heat that's necessary to raise the temperature of 1 gram of water by 1 degree Celsius. So it's defined based on the heat capacity of water, which is why this conversion factor here, 1 kcal, is 4.184 kilojoules. So it's related to the amount of heat necessary to raise water by 1 degree Celsius, which is why it has this familiar value that we have for the heat capacity of water when you convert it between the 2 units. So anyway, we do need to convert the one, and we also need to think about the signs because those aren't directly given to us. So first let's look at Q. And the key word in this problem is that we're absorbing 109 kilojoules. And so that means Q is going to be positive. Whenever the system absorbs heat, that's going to be a positive value for Q. And so that's going to be 109 kilojoules. And then if we look at the work term, W, it 56 kcals done on it. Remember that when work is done on the system, that means work is also positive. So work is going to be positive 56 kcals, but before we add these 2 together, we need them in the same unit. So what we're going to have to do is we're going to convert this to kilojoules. We have 56 kilocalories, and then we're told that the conversion is 4.184 kilojoules per kilocalorie. So anytime you're adding 2 numbers together, they have to be in the same unit. And so when we multiply this 56 by 4.184, we get 234 kilojoules, and now we can add the 2 together. So we take the 109 kilojoules, which is Q, and it's going to be a positive number because it's absorbing heat. We add to that the 234 kilojoules of work, also positive, and that gives us then 343. Okay, and you would just enter the number, of course, not the units. Alright, so that's how we do the first one. We have to just add together Q and W, but we have to make sure we get the signs and the units correct before we do that. Now the next few problems deal with calculations involving heat. So we know that we talk a lot about what's called calorimetry, which is our ability to measure heat using temperature changes inside of a calorimeter. And so this is one type of problem we're going to do. We have a 12.3 gram sample of an alloy, so a piece of metal. We heat it to 98 Celsius and we place it into 54.5 grams of water, which is initially at 22 Celsius. And we're told also that the coffee cup that we're placing the water in has a heat capacity of 9.2 joules per Kelvin. So I think this is the part here, the heat capacity of the coffee cup, that we didn't know what to do with, so we'll get into how we use that. And then if the final temperature of the system is 35 degrees Celsius, what is the specific heat capacity of the alloy? So we have all this information, we have to figure out how to use it. We're giving you the heat capacity of water here, 4.184, that familiar number. So in this type of problem, it's also a calorimetry problem. Remember that then the heat for our system is equal and opposite to Q for calorimeters. So the heat that's absorbed or released by the system is equal to the heat that's released or absorbed by the calorimeter. Because they're opposite, we need to put a negative sign in front of one of them. This equation can be written with a negative sign on either side. And so that's what we have here. And then, so what we're going to do is, in this case, the system is the piece of metal that we're putting into the calorimeter, the alloy as we're calling it here. And then the calorimeter, Q calorimeter, is going to be, just like we do in calorimetry problems involving chemical reactions, it's going to be the mass of the water in the calorimeter, heat capacity of water times delta T, plus the heat capacity of the calorimeter itself, which I abbreviate with capital C, times delta T. Alright? And so this, again, this first term here is going to be the heat that's absorbed by the water in the calorimeter, and this term here is going to be the heat that's absorbed by the calorimeter itself, in this case coffee cup. Alright, so that's kind of the situation here. We're going to lose some heat from the alloy. The alloy is initially at a higher temperature, so when we place it into the water, it's going to transfer heat to the water, and then the heat that's transferred is going to be absorbed both by the water and the calorimeter itself, so we have to add those two contributions together. So now we can just start putting in numbers, and then again for the alloy, the system is just, the heat for the system is just going to be, I should have wrote this earlier, mass of the alloy, heat capacity of the alloy, times its delta T. There's going to be two different delta T's in this. And again, this is going to be our unknown. So we just set the two equal to each other. And so the mass of our alloy is 12.9 grams. So this is going to get, 12.3 grams times the heat capacity of the alloy, which is our unknown, times the delta T for the alloy, which is going to be its final temperature. The final temperature of both the system and the surroundings will be the same, 35 Celsius. So heat is going to stop transferring when the alloy and the calorimeter are at the same temperature of 35 Celsius. And then the initial temperature of the alloy is 98 Celsius. So that's going to be the delta T for the alloy, final minus initial. And we have to put a negative sign out in front of one of these. And then that's going to be equal to the mass of the water, which is 54.5 grams. Heat capacity of water, which is 4.184. Delta T for the water is going to be 35 is the final temperature for the whole thing, and then it started at 22 Celsius. Then the other term that we have to put on the right side of the equation is just the heat capacity of the calorimeter itself. We don't have a mass here. This is just a total heat capacity of the coffee cup, which is 9.2 joules per Kelvin. So we just use that number and multiply it by the delta T to get the other part of the heat that's absorbed by the calorimeter. So 9.2 joules per Kelvin. I was a little bit sloppy with units here, but those should all be joules. And then delta T is going to be, again, the same thing, 35 minus 22. Alright, so now we have an equation where this is our only unknown, the heat capacity of the alloy. And when we solve that, and assuming I did my algebra correct, which I had to take a quick break to do, I got heat capacity of the alloy is 3.98 joules per gram degree Celsius. Okay, so everything in this problem, we need to make sure that all the terms are in joules. So this is our heat capacity of the calorimeter, which is in joules. 4.184 is in joules per gram Kelvin, and that gives us then the answer in the correct unit. So that's what I got for this one. Hopefully I did my algebra right, because I did that quickly, but this is how you set it up. The heat that's released by the alloy is equal to the heat that's absorbed by the calorimeter. So they all have the same final temperature, but they have two different initial temperatures. The alloy, which is initially higher, will have a negative delta T, and the water, which is absorbing that heat, will have a positive delta T. Alright, so that's how I set that one up. It's a pretty typical type of calorimetry problem where we're going to use it to measure an unknown specific heat capacity. Alright, and then this next problem here also dealt with calculating heat. And this one I think is even a little bit more straightforward. It's certainly less steps. And this is just using the equation Q equals mc delta T. Alright, so that's all we're doing here is we're taking 125 grams of ice We're cooling it from minus 23 to minus 46 Celsius, and we're giving it a heat capacity as 2.087. So one thing you will notice in this problem, which may have been a source of confusion, the heat capacity for ice is different than water. Heat capacity depends on the state of matter, so that value that we have of 4.184, that applies to liquid water. In ice, when water is a solid, the heat capacity is different. We'll talk more about phase changes in Chapter 9, but I think we're all familiar with the idea that water can be solid, liquid, or gas, as most things can, and the heat capacity for ice is different than that of liquid water. So we just have to plug the numbers in and get this. So the mass is 125 grams. Probably should have done this one first because this kind of shows us how we use this MC delta T equation. The heat capacity for ice is 2.087. Unless it's the heat capacity of water, we will give that to you if you need it. And we'll do this in degrees Celsius just to be clear on units. And then finally, the temperature change is final minus initial. So minus 46 degrees Celsius minus negative 23. So be careful with signs here. We're subtracting two negative numbers. So that may have been part of the difficulty. But what we get is 6,000. It doesn't say what we're calculating heat in joules. This is going to be 6,000.1 joules. It doesn't say how many decimals to add. That's probably too many, but we'll keep that just to be safe when we enter it in Blackboard. And so we got 6,000 joules for this. So it's just MC delta T, and this should be a negative number though because the system is cooling down. So 6,000 is the magnitude, but the sign is going to be negative if we put the numbers in correctly. And keep in mind that the temperature here is decreasing. So anytime the temperature of the system decreases, Q should be negative. All right. So negative 6,000.1 joules. So the minus sign is important here because it tells us that heat is flowing out of the system, meaning that the system is decreasing temperature. All right. Next problem here is also then dealing with MC delta T and heat transfer between two objects. So we have two iron bolts. One is at 100 degrees Celsius and the mass is 12.7. The other is 56 Celsius with a mass of 15.3. And they're placed in an insulated container. Assuming the heat capacity of the container is negligible, what is the final Celsius temperature inside the container? And so what we're doing here is we're transferring heat between two objects, both of them made of the same material in this case. And so the concept is still the same. The heat term for one of the objects is equal and opposite to the heat term for the other. Okay? Or to be consistent with what I wrote last time, let's put the negative sign out there. So the heat that flows out of one object is going to flow into the other. The value of those heats, the magnitude of those is going to be the same, but the sign will be opposite. So we're just going to use MC delta T twice, one for the first piece of metal, which we call 1, one for the second one, 2. So let's just put the numbers in. So on the one side of the equation, we have minus sign up front. The first iron bolt has a mass of 12.7 grams. Remember that for each of these, Q is equal to MC delta T. That's the only equation for Q that we really have to deal with. And so it's 12.7 grams for the first one. The heat capacity for iron is 0.45, although as I'll show you here, if the two objects are the same, we don't actually need the specific heat capacity. So we can put it in if we're using MC delta T, but we'll see that it divides out. And then delta T for the first object. What we're solving for here is the final temperature. That's going to be our unknown. So it's going to be that final temperature, which is unknown, minus the initial temperature, which is 100 for the first one. And that's going to be equal to MC delta T for the second piece of metal. So the second piece of metal has a mass of 15.3 grams. Same heat capacity because they're both made out of iron. And the heat capacity was given. And again, some confusion with units always. For heat capacity, we can write them as Kelvin or degrees Celsius because it's based on a difference in temperature. And then finally, it's going to be the final temperature minus the initial temperature of the second one, which is 56 Celsius. Alright, so that's how we set up the equation. The only unknown is this is going to be our final temperature, which is what we're solving for. We also notice that the two heat capacities divide out. There's a 0.45 on each side, same heat capacity, same material, so we don't even need that value. We gave it to you here, but this ended up being extraneous or superfluous information. So now we just have to solve for the final temperature. And so the algebra here is a little bit tricky, but we get minus 12.7 times the final temperature plus 1,270, and then on the other side of the equation we get 15.3 times final temperature minus 6.8. So we're just distributing these two sides of the equation, and then when we solve for the final temperature, assuming I did all that right, I got final temperature is 75 point, how many decimal places do they want? They don't specify. It might have been a multiple choice question, but I got 75.96 degrees Celsius, probably too many sig figs there, but that's the number you should have gotten. 75.96 degrees Celsius, assuming I did all that right. And so again, the thing to be careful with here is signs. You need a negative sign out in front of one of the heat terms because the heat terms are going to be equal but opposite in sign. To make them equal to each other, you have to put a minus sign out front. And then also make sure it's always final minus initial using the two correct initial temperatures. So this is kind of the general concept. And whenever we put two objects in contact with each other that have different temperatures, heat flows from the hotter object into the colder object, and the amount of heat that's lost by one is equal to the amount that's gained by the other. Another way to check yourself on these types of problems, if you're solving for a final temperature, either in this case where you're putting two of the same object together with different temperatures, or if we were to put a hot piece of metal into water and solve for final temperature, the final temperature should always be in between the two temperatures that you started with. So one of our iron bolts was at 100 degrees Celsius, one of our iron bolts is at 56 degrees Celsius. The final temperature should be in between those two. If it's not, then you must have did something wrong. So that's a good way to check yourself. Alright, that takes us to the end of questions dealing with heat specifically. Now we're going to talk in things related to delta E and delta H. So delta E is change in internal energy, delta H is change in enthalpy. They're two very closely related quantities that deal with energy changes in chemical reactions, delta H being the one that we more commonly use in chemistry, as it turns out. And here we're looking at the relationship between those two. So we have a chemical equation down here. Sorry, I'll be back in a second. Alright, so this problem, as I said, is dealing with the relationship between delta E and delta H, and we have the chemical equation down here. Now this one is a little bit ahead of where we are. This deals with some concepts related to gas laws as well, which we'll get into in Chapter 8. But we gave you the hint here, P delta V equals delta nRT. And so what we have then is the relationship between delta E and delta H. So delta H is equal to delta E plus P delta V. That's the relationship we should know from learning in class, where this is, again, the derived from the equation for delta E using heat and work and all that. So, which we can then rewrite as delta E plus delta nRT. And then in this reaction, it's run at 298 K, so that's the temperature. We have to find what this delta N term is. R is a constant, so this is the part that may have gotten some people. R is a constant, which we'll talk in more detail about in Chapter 8, but it's the universal gas constant. It's on your periodic table, so the value of it for known. And we want to use the one that's in joules, because this is a problem that's dealing with energy changes in this case, kilojoules. So we have R is going to be this value here, 8.314 joules per mole K. So this delta nRT term here can be also written as the only thing that's changing is the number of moles, delta N times RT. Alright, so what is this delta N they're talking about? Delta N is the change, and we talked about this a little bit in class. Delta N is the change in the number of moles of gas during the chemical reaction. So if the reaction had the exact same number of moles on the reactants and product side of gases specifically, then that would be 0, but if the number of moles of gas is different on the products and the reactant side, it's going to have a non-zero delta N. So delta N is going to be the moles of gas on the product side minus the moles of gas on the reactant side of our chemical equation. So on the product side we have 1 mole of N2 and 1 mole of CO2. And then on the reactant side, the only gas we have is O2, but it has a coefficient of 3/2. So it's going to be plus 0.5. That's our change in number of moles of gas. And so this is going to be, this term here, delta nRT, is going to be 0.5 moles times R, which is 8.314 joules per mole Kelvin. And then the temperature, which in this case has to be in Kelvin because it's not a delta T, it's an absolute temperature, is going to be 298 Kelvin. And so this term here then comes out to, it should be a positive number. This is 1239 joules, which equals 1.24 kilojoules. And so when we put this back into the equation, our delta E was given as minus 742.7 kilojoules. And then this delta nRT term we determined down here is plus 1.24 kilojoules. And so as I mentioned in class, the values of delta E and delta H are not typically that different, so we get minus 741.5 kilojoules when we add those out. And you can see that the values of delta E and delta H are not that much different in most cases, and this is an example of that. So the correct answer here is C. The delta E and delta H are a little bit different in this case, but only by 1.24 kilojoules out of a value of over 700, so it's on a percentage scale a very small difference. Alright, so that's really asked us to extend our knowledge a little bit to really use the information that's given in the problem in combination with what we know to be able to quantitatively relate delta E and delta H. Alright, on to the next one here. This one is asking us to then calculate delta H using delta H of formation. So we have a certain metal this chemical equation here, metal carbonate decomposing to metal oxide and carbon dioxide. We saw some examples of that in class. And we want to calculate the delta H for the reaction if we know the delta H is a formation for the reactants and products. And we have the 3 numbers there. And so this is just asking us to use the equation directly, a very straightforward application of it. Delta H for a reaction is equal to the sum of the delta H of the formation of the products, where M is just the coefficient modifying each product, and then sum of the delta H is the formation of the reactants. So products minus reactants, and we just have to plug in the numbers that were given directly. And here we have coefficients of 1 across the board, so we didn't have to modify them. So on the product side we have 1 mole of metal oxide, and then its delta H of formation is given as, it's the second one here, minus 525.7. And then the second one we have 1 mole of CO2, and then its delta H of formation is the third one here, minus 393.5. Alright, so this is again products minus reactants. This is our MO product, this is CO2. Then we're going to subtract from that. On the reactant side we just have 1 mole of MCO3. And then its delta H of formation is minus 655.2 kilojoules per mole. So it's just products minus reactants. So this part here, this first term is the products, this is the reactants, and we just have to add the numbers together, being careful with signs and all that, as we always do in these types of problems. So what I got for this was minus 264 kilojoules. Okay, so it's just using that equation directly, no tricks to this one. Everything is in the correct units already, kilojoules, and we just have to multiply by the coefficients, which are 1 in each case, and then subtract. Alright, this next question here is what we call a Hess's Law type problem. So I'm going to do a couple of these because we did have a few of these that were difficult. So we're going to do a couple of Hess's Law problems where, again, the idea here is we're looking for the delta H for this reaction down here. And what we're given is two other thermochemical equations, two other chemical equations with their delta H's. So we have to figure out how we add the two chemical equations and then how we add the respective delta H's to get the overall equation that we're interested in. Alright, so the first thing we have to do is figure out how to add these two together. So we have two equations here. And what we'll notice is that our overall chemical equation has N2O as a product, and then this first equation here has N2O as a reactant, and also it has a coefficient of 3 in front of it, whereas we want a coefficient of 1 there. So what we're going to first do is we're going to take the first equation and we're going to flip it, so we're going to take the inverse of it, and then we're going to also multiply all the coefficients by 1 over 3. So what that's going to do is that's going to move N2O to the product side, and it's going to change its coefficient to a 1. So we swap reactants and products, so that's going to be N2 plus water on the reactant side, and then on the product side we're going to have NH3 and N2O, and then what we have to do is multiply all the coefficients by 1 over 3, or divide them all by 3. So N2 becomes 4/3, H2O becomes 1, NH3 becomes 2/3, and N2O becomes 1, which is what we want. And then the delta H for this is going to be minus 1/3 times that first delta H, which is just going to be 10/10 divided by 3. So that's going to be the first equation, how we modify it, and we modify its delta H. And then for the second equation, what we notice is it's going to be a little bit hard to balance this one out using nitrogen, but we see that this one has O2 as a reactant, which is what we want, and that's the only place that O2 appears in either of these two equations. We want to have 1/2 O2 on the reactant side. This equation 2 has 3 O2s on the reactant side, so we're going to have to divide the equation 2 by 6. We're going to take, just 1/6. We're not going to flip it in this case because O2 is already on the reactant side. We're going to take 1/6 times equation 2. That's going to give us then a 1/2 O2 term on the reactant side, which is what we want in our unknown equation. So we're going to take every coefficient and divide it by 6. So we're going to get 2/3 NH3 plus 1/2 O2. And then on the product side, we're going to get 1/3 N2 and water. And then delta H for this is going to be 1/6 times delta H2, the second delta H, which is negative 1531 divided by 6, minus 255.2 kilojoules. Alright, so those are the two delta H's, and if we did our job right, we just have to add the two equations and then add the two delta H's. So let's verify that the two equations add together correctly. So on the reactant side we have 4/3 N2, but that's going to partially cancel out with the 1/3 N2 that's on the product. So in that we have 1 N2. So this 1/3 cancels out, and this 4/3 becomes a 1. 4/3 minus 1/3 is a net of 1 N2 on the reactant side. They don't completely cancel out. We have 1 H2O on the reactant side, but that cancels out with that H2O on the product side. And then on the second equation, we have on the reactant side 2/3 NH3, but that's going to cancel out with this 2/3 NH3. And then we have a 1/2 O2, which is not going to cancel with anything. And then on the product side, the only product that's left is our N2O. So these two equations, after we modify their coefficients, and in the case of the first equation also flip it, add together to give N2 plus 1/2 O2 goes to N2O, and then the delta H for this is just going to be the two added together, 336.7 minus plus negative 255.1. So we just add together the two delta H's. Sorry, 55.2. Sorry, let me write that out again, I forgot units. So the delta H is going to be the first delta H, 336.7 kilojoules, plus the second delta H, which is minus 255.2 kilojoules, and this comes out to 81.5 kilojoules. I do think the correct answer in this was actually 82.0 is how it was written in Blackboard, but this is the only answer that was close to that, so 81.5 would be the precise number in this case. Alright, so again, adding two equations, finding out the delta H by combining the two, and then this next one here is going to be delta H for the following process. This time we have three equations. I lost some subscripts when I copied and pasted this, so all these numbers here after the chemical symbol should be subscripts. I apologize for that. So again, the overall equation we're looking for, let's just go ahead and write it out here at the bottom. We want Fe2O3 plus FeO, this would be called a conproportionation reaction, going to Fe3O4. And the three given equations we have are down here. It looks like they're all formation equations, or at least the inverse of formation equations. And so let's figure out how we can add these together. Now, if we recognize that these are actually related to formation equations, we could also use the delta H of formation method that we used earlier, but let's assume that we didn't do that, and let's just try to figure out how to add these together. So we see that this first equation here has FeO, two FeOs as a product. So let's number them 1, 2, and 3. First equation has two FeO as a product. That's the only place that FeO appears, iron oxide, iron 2 oxide. So if we take this first equation and we flip it and multiply it by a half, that will put 1 FeO on the reactant side, which is what we want. So we're going to take 1 half minus 1 half times equation 1. And so when we do that, we flip the thing, we get FeO with a coefficient of 1 going to Fe plus 1 half O2. And then the delta H for this is going to be negative 1 half times the first delta H, which is going to be this negative 544 times minus 1 half, which is 272. Okay, so that's how I modified the first equation. The second equation here has two Fe2O3s as a product. And in this case, we want one Fe2O3 to be a reactant. This is the only of these three equations where Fe2O3 appears, so we know that we're going to take the second equation, we're going to do the same thing. We're going to take the inverse of it, and we're going to multiply coefficients by 1 half. And so that gives us Fe2O3 going to 2Fe plus 3 halves O2, and we multiply all the coefficients by 1 half. Delta H, again, we're going to take minus 1 half times the second delta H, which is just going to be this number divided by 2 and multiplied by, divided by negative 2. So we get 824.2 kilojoules as the modified delta H for that equation. And then finally, what we want here is this third equation has Fe3O4 as a reactant. We want to have one Fe3O4 as a product, so we're just going to flip the third equation. So that gives us 3Fe plus 2 O2s going to Fe3O4. And then delta H is just going to be the negative of that third delta H, which is going to be negative 1118.4 kilojoules. And then if we did our job right, these three equations should add up to get this equation here. And the delta H will just be the sum of all three of these modified delta H values. So let's verify that they add together correctly. We have FeO and Fe2O3 on the reactant side from these first two equations, and then we have here 3Fe, which is going to cancel out with these three over here. So we have 3 irons on this reactant side, we have 1 here and 2 here, so in that, when we add the 3 together, the 3 irons all cancel out. And then for O2, we have 2 O2s in this equation as reactants, and then on this side we have 1 half plus 3 halves, which is another 2 O2s. So again, on both sides of the arrow we have 2 O2s, so they cancel out. And that leaves Fe3O4 as our only product. So the three equations add together correctly, and then the delta H is just going to be the sum of the 3 delta H's. 272 plus 824.2 plus minus 1118.4. So what we get for that is minus 22.2 kilojoules. Right, so they almost completely cancel each other out, but we get minus 22.2, or what we call this comproportionation of these two iron oxides. Alright, so those last two questions have the same concept. We're adding together thermochemical equations, chemical equations where we know the delta H, and we're adding them together in such ways to find an unknown delta H value. Alright, the last one I'm going to do here, the last couple I'm going to do here are what are called thermochemical equation type problems. And so this first one here asks us to recognize what a thermochemical equation is, and then the next two are going to use that concept. So this was something that I didn't go over in class. We didn't do terribly on these on the assignment, but because I didn't go over it in class in very much detail, I want to make sure I cover it here. So what we have in this case is, the first one we're doing is just we're trying to identify the correct thermochemical equation. So a thermochemical equation is a balanced chemical equation with its delta H. That's all it is. And so all we have to do here is look at the words in the problem and translate it into a chemical equation, and then also then get the correct value of delta H based on what we're told. So here we have 1 mole of KBr decomposed into its elements, 394 kilojoules of heat, sorry, skipping around on me, 394 kilojoules of heat is absorbed. We want to know which of these is the correct thermochemical equation. So the two key pieces of information are, one, we're using 1 mole of KBr, which means we should have 1 KBr as a reactant. We shouldn't have any coefficients in front of KBr because we're told that this is the decomposition of 1 mole of KBr. So that eliminates choices C and D because those have coefficients of 2 in front of KBr. And then finally, the second thing we want is delta H. And so if we have 394 kilojoules of heat absorbed, remember whenever heat is absorbed by the system, that tells us that the heat, which is equal to delta H at constant pressure, is going to be also a positive number. So this should be a positive 394 kilojoules. Okay, so the two pieces of information are that we should balance the equation with 1 mole of KBr on the reactant side, even if that requires fractional coefficients as on the product side. And then we also need to have a positive 394 kilojoules for delta H. So we can eliminate choices C and D because of the coefficients, and then the only one of these that's left that works will be choice A. 1 mole of KBr decomposing, and then a delta H that's positive because heat is absorbed in this case. Okay, so that's kind of what a thermochemical equation is, and how we kind of identify one based on that information. Now let's talk about two questions where you'd use these, kind of in the same way that we would do stoichiometry. So these last couple problems here are going to be a lot like stoichiometry. So the first one here we have the thermochemical equation for the oxidation of SO2 to SO3. Delta H is minus 99.1. With the above data, we want to calculate the enthalpy change when 89.6 grams of SO2 is converted to SO3. So this question is exactly like a stoichiometry problem. We know from the chemical equation up here that when 1 mole of SO2 reacts, the enthalpy change is minus 99.1 kilojoules. Here what we're trying to find out is what is the enthalpy change instead when 89.6 grams of SO2 is converted to SO3. So we're looking for delta H, and we set this up exactly like a stoichiometry problem. We have 89.6 grams of SO2, and just like any stoichiometry problem, the first thing we should do is convert that to moles of SO2. So we use the molar mass of SO2, which isn't given in this problem. It's going to be the sum of the atomic masses, 32.07 for sulfur, 2 times 16 for oxygen. So it's going to be 64.07 grams of SO2 per mole. So we divide by that to get from grams into moles. And then if we look at the balanced thermochemical equation, delta H is minus 99.1 kilojoules. And then the coefficient for SO2 is a 1, so that's per 1 mole of SO2. Alright, so this then converts into kilojoules, and we just have to multiply and divide them and get our answer. So we get minus 139 kilojoules. And again, I don't remember if this is multiple choice or free response, but that would be the number you'd put in, minus 139. Alright, so delta H will still be negative. It's still the same chemical reaction, but we're just figuring out what's the delta H value if we use something other than 1 mole of SO2. And then finally, the last one here is the same concept. Here we're burning carbon to make carbon dioxide. Carbon plus O2 going to CO2, again, all coefficients of 1. If 693 kilojoules of heat is needed from the combustion, how much carbon must be consumed? So here we're told that when 1 mole of carbon is consumed, there's going to be 393 kilojoules of heat released. And if we here what we want instead is 693 kilojoules. So we're going to convert that into the mass of carbon using a setup very similar to stoichiometry problem. So the grams of carbon is we want 693 kilojoules of heat. Remember, in an exothermic reaction, we can think of heat as being a product in some sense. So we're trying to produce 693 kilojoules. And what we see from the balanced chemical equation is that for we need 1 mole of carbon is going to release 393 kilojoules. So this first step allows us to determine how many moles of carbon we need to produce that 693 kilojoules. And then from there we can convert back into the mass by using the atomic mass of carbon, which is 12.01, straight off the periodic table. Alright, and the only thing to be aware of here is that in both of these examples I did, everything had a coefficient of 1, which is why it was 393 kilojoules per 1 mole of carbon, or in the last one it was per 1 mole of SO2. If the coefficient in front of carbon was something other than 1, that would go here in the numerator. So that, remember that this equation tells you how many moles of each substance are reacting, and delta H tells you the heat that's released or absorbed for that many moles. In this case it's 1 mole of carbon, so that's why it's a 1 here, but if it was a 2 or a 3, we'd have to put the appropriate coefficient up in the numerator of this. So don't assume it's always going to be 1, it depends on what the coefficients are for the balanced equation. But this is how we'll set this one up, and what this one tells us then, everything cancels out, we just get into grams of carbon, and that comes out to 21.2 grams. Alright, so if we want to produce 693 kilojoules, we would need to burn 21.2 grams of carbon. This is a lot like what happens when we use coal to produce heat, because coal is basically made out of carbon. Alright, so that takes us to the end of today's review. As always, please come find me if you have any other questions. And I'll see you in class later today.